Welcome back. In this video, you will learn how to calculate the area between two curves. Let's get to it. Alright, so previously in calculus, we saw how a definite integral can be used to calculate the area underneath a curve or underneath a function. But this concept can be extended from finding the area under one curve or one function to finding the area of a region between two curves or between two functions. And so here we have a function f of x, and if we wanted to know the area of this shaded region beneath this function from a to b, we could set up a definite integral as follows. We would have that the area is equal to the integral from a to b of the function f of x times dx. Right? So this definite integral represents the area of this shaded region. And so in the same way, if we have a second function g of x, and we want to know the area under that curve or that function from a to b, we could also set up a definite integral for that region. Right? So the area in this case would be equal to the integral from a to b of g of x times dx. Okay, but the question here is if we put both of these two functions, f of x and g of x, on the same graph, and we wanted to know the area between them, how could we calculate that area? And so here's a graph that represents that scenario. We have our function f of x and our other function g of x, and we want to know the area of this shaded region between these two functions from a to b. How could we find the area of this region using a definite integral? Well, notice if we were to subtract the area underneath g of x from a to b from this area under f of x from a to b, what we would be left with is this region right here, right? This shaded region includes everything underneath f of x from a to b except what's beneath g of x, right? This region right here is no longer shaded like it is in this graph. And so what we can do to find the area between two curves is subtract the area underneath the bottom function from the area underneath the top function. So we could take this integral here, the integral from a to b of f of x times dx, and subtract this definite integral from a to b of g of x times dx. But we can combine that into one definite integral to have that the area is equal to the definite integral from a to b of f of x minus g of x. And then that would be multiplied by dx. Right, so if we want to find the area of a region between two curves, we just take the definite integral from the lower bound to the upper bound of the top function, f of x, minus the bottom function, g of x. And that will give you the area of that region between those curves. All right, so let's take a look at an example problem where we look at how to calculate the area between two curves using this definite integral. Okay, so here's our example problem. We want to find the area of the region bounded by the graphs of y equals x squared plus 3, y equals negative x equals 0, and x equals 1. And so the first thing that I always recommend that you do when you start a problem like this, when you want to calculate the area between two curves, is to graph all of your equations. Right, so let's draw our coordinate plane. I'll start by drawing the y-axis here, and then we'll draw our x-axis, and I will label them as such. So we have the x-axis here, the y-axis here, and now we are ready to graph our functions. And so let's start with y equals x squared plus 3. We know that an x squared function is a parabola where the vertex is at the origin, but since we have this plus 3 here, that means that the parabola will be shifted up 3 units in the y direction. And so if we say that this line right here is y equals 3, then our parabola, or x squared plus 3, will look something like this. Okay, so that's going to be y equals x squared plus 3. And then let's graph y equals negative x. We know that y equals x is just a line with a slope of 1 that crosses through the origin, and so negative x would be the reflection of that line, or it would be a line crossing through the origin with a slope of negative 1, and so that line will look something like this. All right, so that is the line y equals negative x. And so then we have x equals 0. That's actually the same as the y-axis, right? When x equals 0, that would be this line right here. So we don't really need to draw that line, but we have another line, x equals 1, that we should draw on our graph. And so if I say that right here is x equals 1, then our line for x equals 1 would look like this. All right, so that would be the line x equals 1. And so now we can see that the region that is bounded by these graphs is this shape right in here. Okay, so I'm going to shade in this region. This is the region that we are looking to calculate the area of that lies between two curves, right? It is between y equals x squared plus 3 and y equals negative x. X equals 0 and x equals 1 are simply just our bounds of integration, right? This shaded region lies between x equals 0 and x equals 1. And so if we want to calculate the area, let's set up our definite integral. We'll have that the area is equal to the integral from a to b of f of x minus g of x times dx. Now, before we can set this up, we need to determine which is the top function and which is the bottom function, right? Which is f of x and which is g of x. And so in this case, if we're looking at our region and you look from the top down, since we are integrating with respect to x, you want to look from the top down, we can see that the top function is y equals x squared plus 3, and the bottom function is y equals negative x, right? This line is the bottom of our shaded region, and this parabola, or this function, is the top function of this region. And so this is f of x, and this is g of x. All right, so our area will be equal to the integral from a to b, which in this case will be from x equals 0 to x equals 1. So we will go from 0 to 1 of the top function, x squared plus 3, minus the bottom function, which is negative x. And so we'll have negative x, and then we will write dx. All right, and so now all there's left to do is to simplify and solve this definite integral, and we will have the area of this shaded region. And so if we simplify, this will be equal to the integral from 0 to 1 of x squared plus 3, and then this negative and this negative will cancel out to become positive, so we'll have plus x and then dx. All right, so now we can integrate all of these terms by using the power rule of integration, and so we'll have that this is equal to the integral of x squared, and remember that the power rule of integration says that we add 1 to the exponent and then divide by that new exponent, and so we will have x to the third power divided by 3 plus the integral of 3, and the integral of any constant is just that constant times the variable of integration. And in this case, we are integrating with respect to x, that's what dx tells us, and so we will have 3 times x. And then we can use the power rule on our last term, which is x, and so if we add 1 to the exponent and divide by that new exponent, we will have plus x squared divided by 2. And that will be evaluated from 0 to 1. All right, and so if we clean up our work here, we can evaluate this to find our area. And so we'll plug 1 into this expression and then subtract plugging in 0 into this expression. And so if we plug in 1, this will be equal to 1 cubed divided by 3 plus 3 times 1 plus 1 squared divided by 2, and then we're done plugging in 1, right? I just replaced each of these x's with 1, and so that's how we got this expression right here. Now, we want to subtract plugging 0 into this expression, but note that plugging 0 where x is just going to result in 0 everywhere, right? 0 cubed divided by 3 is 0, 3 times 0 is 0, 0 squared divided by 2 is 0. So really we're just going to be subtracting 0, and so that's not going to affect the rest of this calculation. All right, and so if we simplify what we have here, this will be equal to 1/3 plus 3 plus 1/2. Now 1/3 plus 1/2 is equal to 5/6, so this will be equal to 5/6 plus 3, and 3 could be rewritten to be 18/6, so we'll have 18/6, and so if we add 5 and 18, since we have a common denominator, this will be equal to 23/6. And so that is the area of this shaded region between these two functions. All right, and so that is how you can use a definite integral to find the area of a region between two curves. Let's look at another example. So here's our next example. We have find the area of the region bounded between the graphs of y equals x squared and y equals x plus 2. Now this example is a little bit different because, as you notice, we are only given two equations and we are not told the bounds of integration, right? In the previous example, we were told about the lines x equals 0 and x equals 1, but in this case, we are not given any of those extra lines. And in most cases, you are not going to be told the bounds of integration for the region that you want to calculate the area of. And that is because the two equations you are given most likely intersect at 2 points, and those points are going to be your bounds of integration. And so the first thing that you want to do for a problem like this is determine where these two functions intersect. And the way you do that is you set them equal to each other, right? So we have y equals x squared and y equals x plus 2. We can replace y with x squared and then solve for x, and that will tell you the x values of the points that these two functions share. And so if we do that, we'll have that x squared is equal to x plus 2, right? We're just setting our two equations equal to each other. And so let's solve for x. I'm going to subtract x and 2 from both sides of the equation. So we'll have x squared minus x minus 2 is equal to 0. And now we have a quadratic that we can factor, and I believe it factors to be x minus 2 times x plus 1, and that is equal to 0. And the way I factored this is, since we have a quadratic where the x squared term has a coefficient of 1, I just ask myself what factors of the last term, negative 2, when added together, give me the coefficient of the middle term, which is negative 1. So in this case, negative 2 times positive 1 gives me negative 2, and negative 2 plus positive 1 gives me negative 1. And so that's where we get these two factors of x minus 2 and x plus 1 from. All right, so now we can set each of these factors equal to 0 and solve for x. So we'll have x minus 2 is equal to 0, and x plus 1 is equal to 0. And that will give us that x is equal to positive 2, and x is equal to negative 1. And so these two values of x are where these two functions intersect. These are going to be our bounds of integration, where our region that we want to calculate the area of lies between. All right, so now let's draw a graph of our situation to get a better idea of what this region looks like. So I'm going to draw the y-axis here, and then we will draw the x-axis. And so I will label them. We have the y-axis there and the x-axis here. All right, and so let's graph y equals x squared first. We know that that is just a parabola pointing upwards where the vertex is at the origin. And so that will look something like this. And so that will be our function y equals x squared. And then let's graph y equals x plus 2. Y equals x is just a line with a slope of 1 that crosses through the origin. And so the plus 2 is telling us that it is shifted up 2 units in the y direction. And so if this is y equals 2, then our line will look something like this. All right, so that is going to be our line y equals x plus 2. Okay, and so now we can see that the region that we want to calculate the area of is this region right in here. And so now my drawing isn't perfect, but as you can see, if this is x equals negative 1, and this is x equals positive 2, which are the two values of x that we found, you can see that at those x values, our two functions intersect, right? They intersect at this point right here and this point right here. And so those are our bounds of integration because that is where this shaded region lies between. It lies between x equals negative 1 and x equals 2. Okay? And so now we are ready to set up our definite integral to calculate the area of this region. So we'll have that the area is equal to the integral from a to b, which in this case is from negative 1 to 2, of the top function minus the bottom function. Now in this case, if we look at this shaded region, which function is on top? Well, it looks like this line is on the top part of the shaded region, and this parabola is at the bottom of the shaded region. And so that means that x plus 2 is our top function, and y equals x squared is our bottom function, right? You just want to look from the top down and see which function you hit first and which function you hit second. The one you hit first is the top function, and the one you hit second is the bottom function. All right, and so just a quick side note, just make sure that when you do that, that the top and bottom function is the same the whole way through the region. And we'll talk about that in a little bit, about why that's important, but that is the case here. This line is the top function for the whole region, and this parabola is the bottom function for the whole region as well. Okay, so now we're going to have x plus 2, the top function, minus the bottom function, x squared. And then we'll have dx, and now we have an integral that we can now solve. And so if we integrate using the power rule of integration, we will have that this is equal to the integral of x. We will add 1 to the exponent and divide by that exponent to have x squared divided by 2, plus the integral of 2, and that's just going to be 2 times x, right? We just take that constant and multiply it by the variable of integration, which is x, and then the integral of x squared will be x cubed divided by 3, so we'll have minus x cubed divided by 3. And that is evaluated from -1 to 2. Okay, and so if we clean up our work here, we can now evaluate this expression at 2 and then subtract the evaluation of this expression at -1. And so let's plug in 2. This will be equal to 2 squared divided by 2 plus 2 times 2 minus 2 cubed divided by 3. And then we will subtract -1 squared divided by 2 plus 2 times -1 minus -1 cubed divided by 3. And so if we simplify, this will be equal to 2 squared divided by 2. 2 squared is 4, and divided by 2 is still 2. So we'll have 2 plus 2 times 2, that's equal to 4. So we'll have 4 minus 2 cubed divided by 3. 2 cubed is 8, so we'll have 8 thirds. And then we will subtract -1 squared, that's just positive 1, divided by 2. So I have 1/2, and then plus 2 times -1, that will be -2, and then minus -1 cubed, which will be -1 divided by 3, and so we'll have -1 divided by 3. All right, and so if we simplify again, this will be equal to 6 minus 8 thirds minus 1/2 minus 2 plus 1/3, right? This negative and this negative will cancel each other out to become positive. And so if we clean up our work, we can simplify again, and this will be equal to 6 minus 8 thirds, and that's going to be equal to 10 thirds. And then we will subtract 1/2 minus 2 plus 1/3. That is going to be equal to -7/6. And so then this negative and this negative will cancel out to be positive. And so this will be equal to 10 thirds plus 7/6, which is equal to 9/2. And so that is the area of this region between these two functions. Okay, and so that's how you would find the area of a region when you aren't explicitly told what the bounds of integration are. You just have to find them yourself by figuring out where the two functions intersect by setting them equal to each other and solving for x. All right, so for our next example, we want to set up a definite integral that represents the area of the region between the graphs of y equals -x squared plus x and y equals 3x cubed minus x squared minus 11x. Now this is a little bit different because sometimes two functions are going to intersect at more than just 2 points. And so when that happens, it is likely that the top and the bottom functions are going to switch at those points of intersection. And so because of that, we're going to need to use multiple integrals to find the area of the region formed between these two functions. And so let me show you what I mean. If we set these two functions equal to each other and solve for x, we're going to find 3 points of intersection. And so let's do that. We're going to have -x squared plus x is equal to 3x cubed minus x squared minus 11x. And so if we add x squared and subtract x from both sides of the equation, we will have that 0 is equal to 3x cubed minus x squared minus 11x plus x squared minus x, right? These two last terms are just these terms moved to the other side of the equation. And so now notice that we have a -x squared and a positive x squared that are going to cancel out, right? Those will just be equal to 0. And then we have a -11x and a -x that we can combine to be -12x. And so we'll have that 0 is equal to 3x cubed minus 12x. Now, if we want to solve for x, the first thing that we can do here is pull out a factor of 3x from both terms, right? They both have a common factor of 3x. And so if we pull that out, we'll have 3x times x squared minus 4, right? If you pull 3x out of 3x cubed, that 3 is gone, and one of these x's are removed, and so we have x squared. And then for -12x, if you divide by 3x, you are left with -4, and then that x is entirely removed. All right, and so now we have a difference of squares here, right? X squared minus 4, and 4, if you take the square root of that, is 2. And so we can factor that, and we'll have that 0 is equal to 3x times x plus 2 times x minus 2. Right? That is how we factor a difference of squares. And so now, if we set each of these factors equal to 0 and solve for x, we'll have 3x is equal to 0, x plus 2 is equal to 0, and x minus 2 is equal to 0, which gives us that x is equal to 0, x is equal to negative 2, and x is equal to positive 2. And so now we have three values of x where these two equations intersect. And so because of that, because we have more than just two values of x where they intersect, the region that we want to calculate the area of between those two functions or those two equations is not going to have the same top and bottom function all the way through. And so if we take a look at the graph here, here's our function 3x cubed minus x squared minus 11x, and here is our other function negative x squared plus x. And as you can see, here are the 3 points of intersection that we found at x equals negative 2, x equals 0, and x equals positive 2. And we have two different shaded regions that are formed between those two functions. And notice that for each region, the top function changes. For this first region, the top function is y equals 3x cubed minus x squared minus 11x. But after this second intersection point, the top function switches to be negative x squared plus x, right? So the top and the bottom functions swapped after that second intersection point. And so because of that, we can't set up just one definite integral to represent the area of the regions formed between these two functions. Instead, we will have to set up two definite integrals because that top function, f of x, switches with the bottom function, g of x. Okay, and now we can clearly see from this graph which function is on top and which function is on the bottom for each region, but I don't expect that many of us are able to easily graph a third-degree polynomial like this one right here, right? It might be a little bit difficult for you to graph this function in order to determine which of these graphs is on top for the two different regions. And so I want to show you a little trick that you can do in case you're ever not able to graph a particular function and see visually which function is on top. And so if we clean up our work here, what we can do is that for each region between negative 2 and 0 and between 0 and 2 is choose a value of x between the intersection points and plug them into our functions and see which one outputs a greater value of y. Whichever function outputs a greater value of y, that function is on top for that region. And so that would mean that the other function is then on the bottom. And so let me show you what I mean. For our first region between x equals negative 2 and x equals 0, let's pick a value of x equals negative 1, right? Negative 1 lies between negative 2 and 0. And so for x equals negative 1, let's plug that in to each of these equations and see which one outputs a greater value. So let's start with this equation. We'll have y of negative 1 is equal to negative 1 squared plus negative 1. And negative 1 squared is positive 1, but that will be made negative. And so we'll have negative 1 plus negative 1. And so that is equal to negative 2. If we plug negative 1 into our other equation right here, we will have 3 times negative 1 cubed minus negative 1 squared minus 11 times negative 1. That will be equal to 3 times negative 1 minus 1 plus 11. And so we'll have negative 3 minus 1, that will be negative 4 plus 11, and so that is equal to 7. And so our two values of y here are negative 2 and positive 7, and 7 is greater than negative 2. And so whatever function we plug negative 1 into to get 7, that is our top function for this region from negative 2 to 0. For that shaded region, it looks like this function right here, 3x cubed minus x squared minus 11x, is our top function. And so let's set up our first definite integral that will represent the area of the region between these two functions. We'll have that the area is equal to the definite integral from negative 2 to 0, right? That's our first region here, of the top function, 3x cubed minus x squared minus 11x, minus the bottom function, which is this one right here. So we'll have negative x squared plus x, and then we will close that and have dx. All right, so that is our first definite integral that represents the area of this region, but that's only half of that region that we need to calculate. Now let's work on the second region from 0 to 2. Let's see which function is on top for that region. So if we clean up our work here, now we're going to look at the region from x equals 0 to x equals 2. And so this time I'll pick the value of x equals 1 to plug into each of our functions. So for x equals positive 1, if we plug that into this equation right here, we will have y of 1 is equal to negative 1 squared plus 1. and that will be equal to 1 squared, which is 1, but made negative plus 1, and so that will be equal to 0. And then for our second equation here, we will have that y of 1 is equal to 3 times 1 cubed minus 1 squared minus 11 times 1. And that will be equal to 3 minus 1 minus 11. And so 3 minus 1 is 2, minus 11 will be equal to negative 9. And so our two values of y that we want to compare here are 0 and negative 9. And 0 is greater than negative 9, and so we can conclude that this function right here, which is what we plugged 1 into to get 0, is our top function for that region between 0 and 2. All right? And so now we can set up the other definite integral that will complete the representation of the area between these two functions. And so we'll have plus the definite integral from 0 to 2 of the top function, negative x squared plus x, so we'll have negative x squared plus x, minus the bottom function, 3x cubed minus x squared minus 11x. And that is the other definite integral that completes the area of that region. All right, and so if you wanted to know what the area was between these two functions, you could simplify these definite integrals and solve them if you wanted to. But in this case, we just wanted to set up a definite integral, or in this case, two definite integrals to represent that area, just so that you can see that the top and bottom functions can sometimes switch for the region that you're trying to calculate the area of. And of course, that is very common when your functions intersect at more than just 2 points. All right, so that's something to keep in mind as you work on more problems of calculating the area between two curves. Okay, so if you didn't use two integrals here, you would not find the correct area of the region between these two functions. All right, so far in this video, we have only looked at how to find the area between two curves with respect to x, but we can also find the area between two curves with respect to y. And so when we do that, instead of looking from the top down for a function, we are going to look from the right to the left. And so the top function in this case will be the rightmost function, and the bottom function will be the leftmost function. And so let me show you what I mean here. If we have one function, f of y, a function defined with y, the area of this region beneath that function from two values of y, c to d, could be represented with the following definite integral. We would have that the area is equal to the integral from c to d of f of y times dy, right? dy because we are now integrating with respect to y because this function is defined with y. And so in the same way, here we have another function defined with y, and the area of this shaded region beneath this function in the y direction would be equal to the definite integral from c to d of the function g of y times dy. And so if we put those two functions together then on the same graph like we have right here, and we wanted to find the area between those two functions, we could do what we did in the x direction, but now in the y direction. We take the area beneath f of y, which is this region right here, and subtract the area beneath g of y, this right here. Notice that this region between these two curves does not include the region beneath g of y from c to d. And so we take this area and subtract this area to get this area. And so our definite integral for the area will look like this. We'll have that the area is equal to the definite integral from c to d of f of y minus g of y, and that is with respect to y, so we have dy. All right, so it's the same concept. The only difference is now we are looking from right to left instead of from the top down. And so let's take a look at an example problem where integrating with respect to y is actually going to be very useful. All right, so here's our example problem. We want to find the area of the region bounded between the graphs of y equals x minus 2 and x equals y squared minus 4. And so the first thing that we should do is figure out where these two graphs intersect and then draw their graphs so we can determine which is on the top and which is on the bottom. Or in this case, since we're going to be doing it in the y direction, which function is on the right and which function is on the left. All right, so let's first figure out where they intersect. But notice that we have y equals x minus 2 and then x equals y squared minus 4. And so what we want to do is solve for x in this equation so that both equations are expressed in terms of y. so that we can set them equal to each other and then solve for y, which will give us our bounds of integration, or where the two functions intersect. And so all we have to do to solve for x in this equation, so that it's in terms of y, is add 2 to both sides of the equation. And so we'll have that x is equal to y plus 2. All right, so now that these equations are both in terms of y, we can set them equal to each other and have that y squared minus 4 is equal to y plus 2. And so if we subtract y and 2 from both sides of the equation, we will have y squared minus 4 minus y minus 2 is equal to 0. And so negative 4 and negative 2 will combine to be negative 6, and so we'll have y squared minus y minus 6 is equal to 0. And so now we can factor this quadratic, and if we do that, you'll have y minus 3 times y plus 2, and that is equal to 0. And once again, I factored this by looking at my quadratic equation, noticing that the coefficient of the squared term is 1, and so because of that, I can look at the last term, negative 6, and ask myself what factors of negative 6, when added together, get me the coefficient of the middle term, which is negative 1. And so in this case, negative 3 times positive 2 is equal to negative 6, and then adding negative 3 and positive 2 together gives me negative 1. All right, so that is the factorization of that quadratic. Okay, and so if we set each factor equal to 0 and solve, we will have that y minus 3 is equal to 0, and y plus 2 is equal to 0, which gives us that y is equal to 3, and y is equal to negative 2. And so these are the y-coordinates of the points of intersection for these two graphs. And so now let's graph them. Let's actually see what these two graphs look like, and then we'll make note of their intersection points as well. And so I'll draw the y-axis here, and we'll draw the x-axis, and I'll label them. So here's the y, and here's the x. Okay, and so now let's draw each of these graphs for these functions. Let's start with y equals x minus 2. We know that x is a line that crosses through the origin with a slope of 1, but this minus 2 tells us to shift it down 2 units in the y direction. And so if this is y equals negative 2, then our line will look something like this. All right, so that will be our line y equals x minus 2. All right, and then let's graph x equals y squared minus 4. Y squared is going to be a parabola that points in the right direction, or in the positive x direction. So if we ignore that negative 4 for a moment, y squared would look something like this. But since we have that negative 4, we need to shift this graph 4 units to the left in the x direction, or 4 units in the negative x direction. And so I'll remove that parabola, and I'll label x equals negative 4 here, and then I'll draw our parabola like so. And that will be our function x equals y squared minus 4. All right, and so now we can see that the region between these two functions that we want to calculate the area of is this region right in here. Okay, and so what we want to do is determine which function is on the rightmost side and which function is on the leftmost side, right? Because we're going to be integrating with respect to y for this problem. And so what we'll do is start on the right side of the graph and move in the left direction. And what you'll notice is that we hit this line first, and so that will be our top function, or our rightmost function. And then we hit this parabola second, and so that will be the bottom function, or the leftmost function. And so if we clean up our work here, we can set up our definite integral, and remember that our functions intersect at y equals 3 and y equals negative 2, which we can see right here. This is one of our points of intersection, and this is the other. And you can see that this point occurs at y equals negative 2, which is one of those points we found. And this one would be at y equals 3, so I'll label that. We'll have 3 right there. And so our definite integral will look like this. We'll have that the area is equal to the integral from negative 2 to 3, right? Those are our bounds in the y direction. We're going from negative 2 to 3. That is where this region is contained. And we'll take our top function, which is this line, x minus 2, and we will subtract the bottom function, y squared minus 4. Now, remember, they all need to be in terms of y since we are integrating with respect to y. So we can't use x minus 2, we need to use y plus 2, which is the same function, just expressed in terms of y. So we'll have y plus 2 minus the other function, or the bottom function, which is y squared minus 4. And so that will be integrated with respect to y. Okay, so now before we evaluate this, I just want to point out the significance of integrating with respect to y here. Notice that if we were to try to set up a definite integral to calculate this area in terms of x, that if we looked from the top down, the bottom function is not going to be the same, right? On this side of the region, the top function would be the parabola and the bottom function would be this line. But once we cross the y-axis, notice that the top and the bottom function of the region are the same function, right? It would be this parabola, x equals y squared minus 4. The top function would be the positive side of that function, and the bottom function for the region would be the negative side of that function. And so while we could still calculate the area in terms of x, it would actually require using two definite integrals since the bottom function changes depending where you are in the region. And so that is the beauty of integrating with respect to y. Depending on your region, it's going to be easier because you only have to set up one definite integral. All right, because when you look from right to left, no matter where you are in this region, this line is the rightmost function or the top function, and this parabola is on the left or it is the bottom function. Okay, so let's solve this definite integral and find the area of this region to close things out here. So this will be equal to the integral from -2 to 3 of y plus 2 minus y squared plus 4, right? I just distributed this negative through this quantity. And so we'll have dy, and now we can combine these two like terms of 2 and 4, and so we'll have that this is equal to the integral from -2 to 3 of y minus y squared plus 6 times dy. And so if we clean up our work here, and we integrate this expression, we will have that the area is equal to y squared divided by 2 minus y to the third power divided by 3 plus 6 times y evaluated from -2 to 3. Right? We just used the power rule of integration on y and y squared by adding 1 to the exponent and dividing by that new exponent. And then the integral of 6, which is a constant, is just going to be 6 times the variable of integration, which in this case is y. All right? And so let's evaluate this expression at 3 and then subtract the evaluation at -2. And so this will be equal to 3 squared divided by 2 minus 3 cubed divided by 3 plus 6 times 3 minus -2 squared divided by 2 minus -2 cubed divided by 3 plus 6 times -2. All right, and that will be equal to 9 divided by 2 minus 27 divided by 3 plus 18 minus 4 divided by 2 minus -8 divided by 3, right? -2 cubed will be -8 minus 12. And that is because 6 times -2 is -12. All right, and so let's clean up our work again. This will be equal to 9 halves minus 9, right? 27 divided by 3 is 9, plus 18, but -9 plus 18 will be positive 9, and so I'll erase that and make this plus 9, and then we will subtract 2 plus 8/3 minus 12, right? 4 divided by 2 is 2, and these negatives cancel out to become positive, and so we have plus 8/3. Okay, and so then this 2 and this -12 will combine to be -10, and so this will become 8/3 minus 10, so we'll have 8/3 minus 10, and this will be equal to 9 halves plus 9 minus 8/3 plus 10, and if you add all this together, 9 plus 10 is 19, and 9 halves minus 8/3 is 11/6, and so that will be equal to 125/6. And that is the area of this region between these two functions when integrated with respect to y. You could still get this same answer if you integrated with respect to x, but it's going to be a lot easier, as we discussed, if you do it in terms of y. All right, and so with that, that is all I had for this lesson. If you want to see some more example problems, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now, so I will see you next time.